All right, good morning, everybody. How's everybody doing? Doing okay? Good deal. So today we've got some things that we're going to talk about. Before we get into that, though, I want to just mention on your semester by semester guides, you should have seen that I'm giving you an opportunity to get back all of your missed points. If there were any issues that you had and you're not happy with your first score, that's due by Monday the 12th. So there won't be any extensions on that. So if you are not happy with the grade you got, you have the chance to get back all of your missed points. So if you got let's say you got an 80 on the first submission, if you redo it, resubmit it, and it's all like it needs to be, you can get those 20 points back. The way that it is in Canvas is it looks like it's a 0-point assignment on the resubmission. That's because I had to set that to 0 so that it won't add additional points to the course. So whatever points I add in will be kind of like bonus points, okay? So don't think that you're doing it for nothing. You will get back whatever it is. So if you turn it in, I'll look and see what you got on the first submission. I'll read my comments. I'll look to see if you addressed all of those issues, everything's in the right format, everything's complete. And then if everything's fine, I'll go ahead and award those additional points and put them in there, and then you'll be good to go. Are there any questions about that before we move on? Okay, good deal. So it's there. The whole point of the assignment isn't to give points or take away points, but for you to have a good document to take to your advising sessions, a good document to have with you during your time here. And so that's what I want you all to have. Okay, so I'm going to give you your opportunity to get those points back. One thing that I do need to do before we get started in today's lecture is I need to retake the seating chart. So you might remember the first day of class, I kind of took a picture. Some people were here, some people weren't. In this era of contact tracing, we're supposed to be taking a better account of where people are. Put your name, print it please, and then your ID number, okay, right beside it, and then pass it to the person down, and then I'll come down this way and pick them all up, and that way I'll have a seating chart for the class. Just you on this one. Okay, good. Just you on row 5. Look at that. Thank you. All the way back here. There we go. Gotcha. Kind of work their way. You all done? Thank you. Thank you very much. I'll come back and get it. Thank you. Thank you so much. Thank you. Appreciate it. Thanks. Thank you. Thank you. See, I already got yours. Get these two. Thank you so much. Thank you very much. always dislike this room. Walking up and down the steps aren't quite my stride, so I kind of feel kind of weird. All right, so we had basically three things that I wanted you to do today to watch before we came into class. One was the discussion with Stephen Knowles. What was the doing? Anybody want to take a guess? Yeah. Yeah, that's right. A lot of people who end up thinking about majoring in a science like chemistry, biochemistry, or polymer science, or whatever the case may be, typically think that undergraduate education is going to be preparation for something like medical school or graduate school or some type of professional continuation. And that's certainly true. I mean, a lot of people do that, and there's absolutely nothing wrong with it. Stephen Knowles, however, decided as he became a senior that he had had enough school. He was ready to live his life, right? And he decided to go off and find a job, and he did. And he found a job locally. He started off working at Georgia Pacific here. So Koch Industries, big conglomerate, as you all know. They own Georgia Pacific. Oh, you're fine. Okay, so they own Georgia Pacific. He gets a job and right out of his undergraduate. Okay, so he had basically a bachelor's degree in biochemistry. He did research with me. I'm an organic chemist. We do some things that are bio-related, but he did research with me, and he took all of that experience and was able to get a technician level job at Georgia Pacific. Is he still at Georgia Pacific? He's still with Koch Industries, but he's no longer with Georgia Pacific. He actually recently moved to Texas. I think the name of the company is still a Koch Industry, but I think it's Forest Hills Resources or something like that. They do a lot of polymer work. As he said, he spends a lot of his days characterizing polymers these days. Got none of that experience as a biochemist, got none of that experience certainly in my lab. I don't do anything with polymers other than use plastics, okay? But he was able to take that experience that he had with the experience that he got at Georgia Pacific, he was able to move up into another company. In other words, I want you all to know that there are transferable skills in this major that you can, with some experience, move up in a company. Even if you decided, I'm going to graduate in 4 years, I'm going to get a job. There are opportunities around there. Now, right now, things are tough across the board because of COVID, and he even talked about that. But even during COVID, he was moving to a new job because there was a need for people like him in the workforce, okay? He works in a lab every day. That's what he does. He's not a project manager. He's a laboratory technical individual, which we had talked about from the CNE news article, what was that, 2 weeks ago now? When he left, I don't remember his exact figure that he got for going to work at bachelor's degree, $23, $24 an hour, whatever that comes out to be a year. I'd have to do the figuring in my head. I don't have it right off the top of my head. But it wasn't a bad salary starting off with a bachelor's degree in Hattiesburg, Mississippi. That's where he started, okay? All right. So yes, he does what he would call molecular sensors, right? Why would this area of research be important broadly? Sure. Absolutely. So there's a number of situations where you want to know what's in something, right? So it could have environmental implications, right? You are a scientist going out studying things in the environment. You might want to know what types of heavy metals are in a particular soil sample, a particular water sample. You need to be able to detect that. We've had ways to detect this for many, many years. So what's novel about what he's trying to do? He's trying to make it easier to detect these things, right? How can we detect them without having to go through a large amount of processes to determine how much zinc or lead or whatever the case may be in a particular sample, right? But it goes beyond just the environment, right? You go to the doctor and they run tests. Those tests are about what's in your system, right? And sometimes you do need to know what's the chloride ion content in the blood. Sometimes you need to know what are the heavy metals that are in a blood or urine sample. You need to know these things. There are a number of diseases that are caused by metal deficiencies or excess metals, many of which you get through your diet, right? Why did he have these pictures of plants here, this Venus flytrap and these colorful flowers? No, that's exactly right. Yeah. So what I want you to take away from this is that people, scientists, take away from some of their inspiration from nature. You know, imagine watching a Venus flytrap work, right? And thinking that could be a way in which we could actually entrap things out of a sample, right? Could we build a molecule that would function like that, right? In terms of the flowers, the pH depends on what's going on with the color, right? It's an indicator. You can tell the pH of the soil through these flowers. You can kind of get a range of what the soil pH must be, right? And so, again, deriving inspiration from nature to come up with chemical processes that actually solve real-world problems, okay? So he's interested in looking at anion recognition, cation recognition. He's also got some interest in things that could have importance in molecular imaging, for example, things that could have relevance to the medical field. And in fact, one of the students that you all will be hearing from, who was a former Golden Eagle, who is now an MD resident, actually did her research with Dr. Wallace. He's an inorganic chemist. She was a biochemist. They collaborated together to work on a set of projects that ended up being relevant to her goals of going into the medical field. Okay? I want you to remember that if you're a chemistry major, chemistry emphasis, you can do biochemically related research. If you're a biochemist, you can do chemically related research. This is an interdisciplinary enterprise. Okay? And people collaborate in a variety of ways. Typically, we take on these labels of chemist versus biochemist, largely for historical reasons. Okay? Historically, biochemistry programs were in medical schools. Chemistry programs were on the university side. And many universities that don't have medical schools will put chemistry and biochemistry together in one unit, if you will, a school, a department, whatever the case may be. And it works. We share a lot of things in common. We have some things that are different, obviously, but a lot of things are in common. Okay? What's common of all sciences? Math would be a common discipline that we rely on. That is certainly true. Absolutely. Pardon? They're all difficult. We're going to talk a little bit about that, aren't we? We're going to talk about difficulty a little bit. Okay? And so you all, I hope, watched the video, Star Talk, Science is Hard, with Neil deGrasse Tyson, right? Very famous astrophysicist, on the news a lot. You all have probably seen him in a variety of popular media sort of scenarios. There are some people who have a gift of being able to communicate science to the public. And for whatever reason, in my opinion, physicists tend to be better at this than most. Neil deGrasse Tyson, Carl Sagan, Richard Feynman. These individuals have this, for whatever reasons, physicists seem to have a very good knack at communicating science to a broader population than, say, typically a chemist, although there are a few chemists that are actually quite good at it. Okay? But the more popular ones tend to be physicists. He said science was hard, and he went through it, right? And he was talking about discovery of planets and what we thought were comets and yada, yada, yada. And he talked about a time frame that basically was, what, about 300 years or something like that, right? And they started off talking about math, and then he said, no, that's not really what I'm talking about. What was difficult about science? Mac?
We're always challenging how much about human understanding. We're always trying to get past it, but we don't really always know where we currently are.
That's right. We are pushing the boundaries of knowledge in science all the time. If you want to be a successful scientist, you are not going to be doing the things that have been done. You're going to be doing things that are new. You're going to be challenging our understanding of the world as we know it now. You're going to be adding to the body of knowledge, right? Science is not a discipline. I know that sounds weird. Science is a method and a procedure, or a process. What do we call that process? We call it the scientific method, right? That's exactly right. I don't care if you end up being a biology major, a physics major, a chemistry major, a polymer science major, a psychology major. All of those things are sciences, and they all share in common one scientific method. You all go to class, and this is unfortunate, I think, and I'm trying to bring this to you now so that you can have a little bit better understanding of this. When you go to your classes, you're going to learn content. You're going to go to your general chemistry class, and you're going to learn about stoichiometry, you're going to learn about heats of reaction, you're going to learn about all kinds of things. You go to your English class, you're going to learn a lot of English content kind of things. But science is a process, and in no class do we really sit down and talk with you about the scientific method. And I think that's a shame. I think it's a shame that we have reduced science to memorization or application of content. That's important, don't get me wrong. But it's not going to save the planet. Or improve our lives, or improve our health. What is, however, going to assist with those types of big questions that we have is the scientific method. Okay? So, when we think about the scientific method, you all probably learned some things in grade school or high school about the scientific method. and then you probably go to a research lab at some point and you go, did we ever really use the scientific method? It kind of falls to the back. We don't always push it to the front, especially for undergraduates. You might go to a research lab with Dr. Wallace or somebody and they'll say, work on this project. Work on this piece of this project. But you may not have a complete understanding of where the scientific method falls into this, because over time, right, this has come out to be. What's the first step in a scientific method? Anybody want to take a guess? Pardon? Hypothesis is one of the steps, but it's not the first step. Mac?
Bigger question.
Okay, we have some sort of question. That's close. But how did we come up with that question? All right, we made some sort of observation, right? We observed something. So we'll call the first step observation. You woke up this morning and you observed X. And that caught your curiosity. Right? What could X have been? Could have been anything. It could have been you woke up, you put your pod in your Keurig, you closed it, you went to go take your shower, you came back and no coffee was made. You made an observation. Okay? And that led to a question, right? I think it was Mac that said question, right? That's the second step. You form a question. What might the question be here? In that example of the Keurig. Why didn't the coffee maker work, right? Why didn't the Keurig work? I mean, a simple thing as your machine not working to make coffee, we're going down the scientific method here, right? You made an observation. You formulated a question. Now what do we have to do? We have to form a hypothesis. Oop, if I can spell it. Hypothesis is that thing which separates science from all other disciplines. In my humble opinion, it is what sets science from the arts. It is what sets science apart from the humanities. Okay? That's not to say that those things can't use the scientific method. They absolutely can. But the hypothesis is what is central to the scientific method. If you are not forming hypotheses, you are not doing science. You've probably heard the term pseudoscience. That is where you have formed, you've gone through a bunch of processes, but you really don't have a hypothesis. Okay? Can anything be a hypothesis? What are some criteria for a hypothesis? I'm sorry, I couldn't hear.
It doesn't have to be a if-then statement.
It could be that. It could be an if-then statement. What else could it be? Okay, it's got to be a statement that can answer the question that you formed. Okay. What else? Pardon? We have to be able to draw a conclusion. Yeah. That's right. It has to be testable. You all were getting at it. Right? A hypothesis must be testable. Very, very important. I have heard people come up with hypotheses that aren't hypotheses. I'm on a committee right now for a graduate student. I read through the document that they have to present this week, and their hypotheses are not hypotheses. They are goals. Goals are different from hypotheses. I have a goal to lose a little weight. That is not a hypothesis. But I can make a hypothesis about what I might be able to do to lose weight, right? So a lot of times scientists, especially younger scientists, will confuse goal and hypothesis. They are not the same thing. necessarily. Okay? So it has to be testable. Very, very important. Must be testable. What's the fourth step? Mac has just formed a hypothesis, and now Damien wants to do what with that hypothesis? They're working on a team. You want to do some sort of experiment, right? So exactly, we're going to do an experiment. Or as some people just say, we want to test the hypothesis. And that gets to the if-then statement. If-then is kind of a prediction. So we'll quite frequently we'll form a hypothesis, we'll make a prediction from that hypothesis, and then we will test that. Okay? Can you do experiments without a hypothesis? You can't? You can. You can actually do experiment. You could. You could run an experiment and not even know what the hypothesis is. Chances are when you go into your Chemistry 106 lab, you probably really don't know what your hypotheses are. You've been given a cookbook experiment to go run. And I think that's a shame. But it's just the way it is because of time. It's hard to give a student a hypothesis, give them 2 hours and say, go figure out how to test that hypothesis. Right now, when you're going into your lower level laboratories, your 106s, your 255s, your 256s, right? You're learning techniques through the use of experiments that have been well established so we know the results, right? We want you all to leave with, I know how to do a titration, I know how to properly weigh things, I know how to work with a reagent that might catch on fire if it gets exposed to air. You're learning techniques at this point when you go into the laboratory. Where in your undergraduate education are you really going to experience science? It's going to be in your undergraduate research. You're going to go into a research lab. You will probably be given a piece of a project, and you will be collaborating with your advisor on discovering new knowledge. I've got 3 undergraduates doing research with me right now, and quite frequently they'll come to me and they'll say, well, what was the answer supposed to be? I don't know what the answer is supposed to be. We're doing this for the first time. It's not like your general chemistry laboratory. We don't come into my research lab knowing what the outcome is. We have made a prediction based on our hypothesis, and now we are testing it. And when that test turns out to be positive or negative, we have to make a decision, right? And we have to think further about it. So again, that's why we have, as part of your requirements in this program, undergraduate research. That's where you are really going to learn science. That's where you're going to learn why it's hard. Hard should not mean to you avoidable. You should not avoid things that are hard. You should embrace things that are hard. That's where we have advances. Okay? That's where we have advances. So Damien has done his test, his experiment. Now what do we do? Record the data. Okay, yeah, we're going to record the data. Let's just say that that's part of the experimental process. Okay, we're going to draw some sort of conclusion from that data, and we're probably going to iterate. Okay? What do I mean by that? We're going to go back and do it again, aren't we? As scientists, do we do an experiment once? No. Why not? It could be. It very well could be. There is the possibility that when I go into the laboratory and run an experiment, that I got the result that I got out of chance, and that A did not influence B at all. So I'm going to go back and I'm going to repeat that experiment. And I'm going to look at the data, and I'm going to compare those results, and I'm going to iterate again. Most scientists will tell you that at minimum you need to run an experiment 3 times. And let me give you an example. I've got a graduate student, fairly new graduate student. He's been with me since January, and of course COVID, right? So how much time has he really been in the lab? Not a lot yet. He came to me in the summer when we came back to class, and he ran an experiment, and he came back and he said, I don't know that this is going to work very well. I got a very low yield of the product. Would it have been wise for me to say, well, let's scrap that and move on to something else? Why not? Number one, he was a brand new graduate student. He's gaining his synthesis legs, as we say. He's learning the techniques. Do you think he probably had the best technique the first time he tried something? Absolutely not. Nobody does, right? So I said, well, we got some yield. It wasn't something you'd want to hang on your refrigerator as a proud moment, but it was, we got the product. It's just that you got it in very low yield. So did I have him change the experiment, or did I have him just go back and replicate it again? We just did it again. I wanted to test him as the variable. His skills as the variable. Before we start changing, adding different things or trying different additions or whatever the case may be, I said go back to the lab and do it again, as you've written down in your notebook. And guess what? The next time he came to me, he said, hey, I got an 85% yield. Could have been an accident, right? He could have misweighed something, or he could have been getting better skill sets, right? He's already done it once. He kind of knows what to expect. So what did I do? I sent him back to the lab and told him to run it a 3rd time. He came back and he said, hey, I've gotten a yield that's about 85, 90% again. Then I started to believe that the chemistry itself was going to work like we wanted. It was a situation where his skill set just needed to be tweaked, right? So we didn't go through and change the experiment. Now, I have had situations where students have come to me 3 and 4 times and said, no matter, I've done it the same way 3 times, I'm getting nothing. Now we start to think about what can we change in the procedure. Because now I'm pretty confident that the individual is probably okay with their technique. I've observed them, right? And so we iterate. It's a very important piece of the puzzle, okay, is iteration. Now, most people would say that's the end of the scientific method. I say there's a 6th step, and what would that 6th step be most likely, in your opinion? Okay, I'm going to say disseminate, which can mean publish. Okay, publishing is how scientists today typically like to disseminate their results. Is it the only way? No. You can go give talks. You can give lectures like I'm giving right now. I do that at least a couple of times a year. I go to a university and talk about the science that my students are working on. I'm disseminating to the public, the broader public, even though it's the scientific public, about what we're learning. Okay? Why is that important? That's right. Other people can iterate on it. Other people can challenge it. I have been at talks where I have talked about the data that we collected, the conclusions that we drew, And I've had really good conversations with folks after that talk where they said, you know, another interpretation of that data may be, I hadn't thought of that. And so that gives me an idea to go back and test my hypothesis from a different angle. Okay? It is very, very important. It is central to the scientific method. It is central to the scientific enterprise that we disseminate our results. Even companies disseminate their work. They are secretive about it at some point because they want to protect their intellectual property. They want to be able to make a buck. It's perfectly fine. But even companies at some point will publish what they have done in the form of patents, right? So they're getting ready. They've been working on this super material, okay? Something that's going to, make aircraft lighter and faster and more fuel efficient, whatever the case may be. They want to patent that so that they can have a corner on the market for 20 years, right? And when they submit that patent, that is a form of publishing. People can go in and review patents. Other companies can go in and review patents. It's important. They probably went in and reviewed other patents. Many companies actually require their employees to publish. If you go work for Merck, I interviewed with Merck when I was out of graduate school. And one of the requirements for keeping a job with Merck is you had to publish so often. And they gave you so much time every week to work on any project you wanted. But you had to publish. You had to contribute to the scientific literature. Okay? It's important. Okay? So we can disseminate research through publications. We can disseminate research through patents. We can disseminate research through presentations. You can actually disseminate your research over coffee. I've seen people do that. Little coffee chats. Okay? This is what sets what you're doing apart from what some of your friends are doing in their majors. Okay? It is a process. It is a method. You are learning a lot of content right now. We're stuffing your head with a lot of content. But what's really important is this. This is the most important thing about science. This is how we know what we know. Because we've shared it with people, it's been challenged, it's been tested. You all are seeing the scientific method in process right now with COVID-19. And you're seeing it being politicized on both sides incorrectly. Okay? But Dr. Fauci, for example, at one point had a hypothesis that wearing a mask was not going to be the best thing for you. That was the best data he had at the moment. And as we got new information, he iterated on that, and his position changed. Does that mean he's wishy-washy? Absolutely not. It means he's a man of science. He's following the data. He's making the best recommendation he can at the moment. It just so happens that this one has to deal with life and death for people, as opposed to the research I do, which doesn't deal with life or death of people. And thank goodness. Okay? But people made an observation. People were getting sick. They asked a question. What could it be? They formed a hypothesis. They tested that hypothesis through experiment, and they have reiterated. And they have disseminated. And because they have disseminated, we have been able to take action to help prevent the spread of the disease. It is very, very important to be able to do this. And yet, through your scientific training in your curriculum, we're not focusing on this enough. I want you to think about this. This is the important thing. For those of you who are going on to medical school, I've heard some physicians say, we're not scientists. And I've heard other physicians say, well, yeah, we are. Right? How does the scientific method line up with when you go to the doctor?
You see that something's wrong with someone, you ask why, you predict why, predict what's wrong with them.
Yeah.
You perform a test on them to see if that is indeed what's wrong.
Yeah.
Then you revise it. If it's not, if it matches up.
That's right. I would say the only thing that they can't do is disseminate
Yeah, maybe
as a physician. Now, if they're doing medical research, that's different, obviously, then it would be the same. But when you go to your doctor, an observation has been made, I don't feel good. The question might be, why don't you feel good, right? The hypothesis may be, oh, there's a lot of COVID going around. The test is the swab up the nose, right? Then you get a result. That result comes back positive for COVID. Does that mean that COVID is why you don't feel good? Not necessarily. A lot of people who are asymptomatic never feel bad from COVID, right? So even though a piece of data seems to support the hypothesis, it doesn't necessarily mean that the hypothesis is correct, right? What is central to testing a hypothesis? You must be able to falsify the hypothesis. That is what is critical. You do not design an experiment that proves your hypothesis. You want to develop an experiment that is designed to disprove your hypothesis. Again, something that separates the hard sciences from what I will call pseudoscience for the moment. When I sit down and design an experiment with one of my students, we think about a test that can not confirm my hypothesis, but that can disprove it. Okay? That's very, very important. You can never completely prove a hypothesis. Why? That's because science is hard, like Neil deGrasse Tyson was saying. There's something that we may not know yet that may come back later and say, oops, what we thought, even though everything supported it, was incorrect. Right? All of the data at one point suggested that there was a planet Vulcan. They never found a planet Vulcan. Right? They found that there was some bad data. Right? And they were able to show that actually the world worked as it should once they took that into account. Okay? So it's very, very important that as you develop a hypothesis, that you develop it in a way that it can be disproven. Right? So I run an experiment. The result supports my hypothesis. I can't run out and say this must be true. In another iteration, I might try a different experiment to interrogate my hypothesis. I know scientists whose entire careers have been built on a single hypothesis, and they've spent 20 or 30 years interrogating that hypothesis from different points of view. And you could get to although I don't know anybody in this boat, you could get to at the end of that 30-year career and do that one experiment that said everything that you had studied in the past was false. That's science. That's why it's hard. Well, as humans, we like to think we're right. Right? When I develop a hypothesis, I don't sit there and go, well, let me put the easiest hypothesis out there that could just easily be disproven. I put together something with a lot of thought, right? I put together something that I'm invested in. I have a stake in that hypothesis. I have a bias towards that hypothesis. That's why I have to disseminate my results, right? So if I form a hypothesis and I've been testing it, I want you to look at that so that you can check me. No, Dr. Masterson, you're too attached to this hypothesis. I've done experiment Y and Z, and none of those things support your hypothesis. Your hypothesis predicts that Y and Z should be correct, and they're not. So your hypothesis must not be correct. Yeah, but I've done A, B, and C, and it supports the hypothesis, and we will have a debate. And I'll probably start attacking your position on, well, your experiment must be wrong. You must have some issues with your experiment. My experiments are perfect, right? And you'll counter that, and we'll go back and forth. There are some classic debates in the chemical literature. We don't do it anymore like they used to. But there were some classic debates between George Olah, who was a Nobel Prize winner out of California. I think he was at, was he at UCLA? I can't remember exactly where he was at now. But he won a Nobel Prize. And Herb Brown, who also won a Nobel Prize. And they went back and forth at meetings. The people who were around at the time talked about how they just berated each other at meetings about a position on their work. And it even went into the literature where one person would publish and another one would publish a rebuttal to their experiments. And they went back and forth for years on their scientific works. That's not a bad thing. In fact, as I understand it, they kind of liked each other. But they went back and forth for years on this. Now, I certainly do not encourage people to be, a butt about it. We need to be professional, and I think some of those have gotten a little too personal at times in the past. But nonetheless, that is the scientific method. Okay? I wanted you all to have this because I really do feel like high school education and your beginnings of your college education don't focus enough on the scientific method. It is what matters. Okay? And just like I said, if you end up being a physician, you're going to be doing this. You're going to make an observation. You're going to ask a question. You're going to form a hypothesis. You'll call it a diagnosis, but that's what it is. And how does a physician experiment on you? Your actual tests, and
See how you feel in a week.
after they give you some sort of treatment, right? Oh, I think what you have is a bacterial infection. Here's an antibiotic. Come back and see me in a week. That come back and see me in a week is not about getting another fee from you. Okay? It's about following up and iterating. Oh, Mac, you came back after a week. I thought you had a bacterial infection. I just gave you a Z-Pack. You should be feeling better. You're still running a fever. Does that support my hypothesis? No. Probably just disproved my hypothesis, depending on the bacteria, right? So now we form a new hypothesis. And we iterate, and we do another experiment. Okay? So I am very much so in the camp. I do teach part of the MCAT prep course, and I always teach this to students, that even though you're going to go off and be a physician, you are going to use the scientific method, even though you don't use it by name. People will come in with a problem, you will make an observation, you will form a question, you will form a hypothesis, you will test that hypothesis, and you will iterate. Okay? So I think it's very, very important that you have a fundamental understanding of the scientific method. And I am at the end of the things that I wanted to talk about today. I wanted you to understand that while science can be considered hard, it's also very, very rewarding. I've had students in my research lab that did something that nobody else has ever done. I've had students make molecules that have never been made before. Undergraduates, actually. And I looked at one time, and it was just amazing to watch her face. I looked at one time and I said, do you know that more people have walked on the face of the moon than did what you just did? You have that opportunity in science, even as an undergraduate, to do things that nobody else has ever done before. And I find that exciting. Yes, it's hard. It's a challenge. But, man, you talk about a thrill. Being able to go into a laboratory and make something that nobody's ever made and study it and see what it's capable of, what it can do. That's exciting work. And if you find that exciting, you're in the right major. All right, everybody, just exit out the back as normal. I will have things up by the end of the week. Remember, we got a hurricane coming this week, so keep an eye out for that, and stay safe, everybody.